All right, hello everyone. Welcome to AP Review number 6. We are going to be talking about related rates and kind of mixing into some of that again here, some differential equations. Primarily focused on related rates. You'll see some differential equations pop up too for sort of continued review. All right. Just as a quick reminder of sort of our basic steps of approaching related rates problems. When you see a problem that looks like it's letting you know it's a related rates problem, we'll talk about how you know that in a second. We first off need to list our knowns and unknowns. I like to just pop those things uh, right on my page, write myself some notes. So I'm going to write down my unknowns and my knowns. You probably remember that I also like to write out like what my question mark is. What is the thing I'm shooting for also. Then I want to write an equation or find an equation, because sometimes we're getting given one. Write an equation that relates our variables. All right. Kind of gotta look, what is the kind of Venn diagram intersection of the variables and information that we're given. Then we will differentiate that equation. And key here, because we're dealing with related rates, everything is a function of time. So we'll differentiate the equation, yes, but the real key here is with respect to, so WRT, I'll use that abbreviation, with respect to time. Everything's going to be a d something dt. Every time I take a variable or derivative of a variable that's changing, differentiate the equation, I'll do it with respect to time, d something dt. If a variable is not changing, then I can just count it as a constant and deal with it that way. Then I'll substitute or sub in knowns and solve, okay? So let's take a look at this this practice question right here. The radius of a circle is increasing at a constant rate of 0.2 meters per second. Radius of a circle is increasing. It's increasing, and this is a rate. So let me give that a name. The radius is increasing. I can call that dr dt because it's a rate. The radius is increasing, dr dt. It's increasing, so dr dt, the rate of change of the radius, is going to be positive. The rate is 0.2 meters per second. I'll just write that down. What is the rate of increase in the area of the circle? What is the rate of increase in the area of the circle? That sounds like what I want to search for. That's the what question. The rate of change of the area of the circle, we can call dA dt. And I want to know what is that rate of increase. What is that dA dt of the area of the circle? When, I like to write out this way, when circumference, I'll call that C, equals 20 pi. Okay. So I want to know something about area. How is area of the circle changing? And I know something about the radius of the circle, right? dA dt. What is dA dt? So now I have my knowns and my unknowns. I need to write an equation that relates our variables. The variables that looks like are going to be really important here are our area and our radius. The circumference is a when kind of thing, so I'm going to hold off on it for now. So what is an equation that relates area and radius? Well, that's easy. This is a circle. Right? If it helps, you can diagram it out. We got a circle. We have a radius that's increasing. And then we have an area. The area of a circle is pi r squared, right? So area is pi r squared. This relates a and r, our two variables up here. They're going to be changing with respect to time. So a couple ways we could do this. One, we could say, okay, well, I need to get down to dA dt, so let me differentiate this equation with respect to time. What is the derivative of area with respect to time? Derivative of area with respect to time. Derivative of a is 1, but with respect to time, 1 dA dt. Equals pi r squared. What's the derivative of r squared with respect to time? 2r. So this will be 2 pi r, because pi is a constant. 2 pi r. But r is a function of time, so I'm going to use my chain rule. R is its own function of time, so it's dr dt. There's our key to related rates. It's like implicit differentiation. We're taking the derivative of everything on here, all the variables, with respect to time. So when we take a derivative of one, we do it like normal, but then we'll multiply by dr dt, all right? Because that variable is changing with respect to time. All right, so here is our derivative. We see dA dt has appeared. I see dr dt in there. I have this 2 pi r. So one way you could approach is say, well, I need to know what r is then. How do I figure out what r is? I could use the circumference thing. Because what is our formula for circumference? Circumference is, right, pi times the diameter, or 2 pi r. circumference is 2 pi r, right? Circumference is 2 pi r, so 2 pi r is going to equal 20 pi, and I could solve for r. Plug that in. But you might be a little sharper than. You may say, well, 2 pi r is going to be 20 pi in this situation, because circumference is 2 pi r. 2 pi r, the circumference of the circle, is 20 pi. Look, there is 2 pi r right there. So I can actually shortcut this and say dA dt is going to be equal to 2 pi r, which is the circumference, so that's 20 pi, and dr dt, which is 0.2. When I multiply all that together, right, I will get 4 pi. It will be meters per second squared because we're talking about how the area is changing, and area is, sorry, not meters per second squared, meters squared per second, because area is meters squared, and is changing over time, which our unit of time is seconds. You could have also kept the units here, that the radius units here are meters, the dr dt units are meters per second, so meters times meters per second gives us meters squared per second. All right. So here's an example related race question kind of on a more basic level. Sometimes we need these kind of helper equations to help us get through. I want to use the rest of our time to look at two free response questions that include related rates, but also mix in some other topics, okay? So let's take a look at one here. I know we've seen part of this already. We're going to see the whole thing now. Train runs back and forth on an east-west portion of a track. So we can kind of think about it like this. We got a train track. This isn't AP art, Nina, so we can just do it like this. We can draw a beautiful picture of a train if you want to, though. I should stop saying that. Do what you want, Nina. Here is our train running back and forth east-west on a section of the track. Train A's velocity is measured in meters per minute over here. Given by a differentiable function, it's a differentiable function VA. That's our velocity, train A's velocity. Where time t is measured in minutes, selected values of V of A are given here. A says, find the average acceleration of train A on the interval 2 to 8. Okay, interval 2 to 8. So we're asked about the average acceleration. We're given something about velocity. Acceleration is the slope of velocity. We're given points, so this just becomes a slope formula thing. I need to find V of 8. I should say, if you want to for this FRQ, if you would like, if you're feeling this, go ahead and you can pause the video and try things on your own if you want to too, and then come back and check your work. V of 8 minus V of 2 over 8 minus 2. Our units for V we'll add in our next step here. V of 8 is negative 120 minus V of 2, which is 100. And the units for velocity are meters per minute, right? Meters per minute. Over 8 minus 2 is 6. Units for that, those are times, is minutes. You can actually just leave it like this. You don't have to do anything else with it. But if you wanted to, we could say this is a negative 220 over 6 meters per minute. Per minute is acceptable, or if you want to simplify all the way down, but I discourage you from doing that. Please, I would highly recommend not doing that. We could simplify it all the way down to negative 110 thirds meters per minute squared. All right, here we go. What does B say? B says, do the data in the table support the conclusion that the train's velocity is a negative 100 meters per minute at some time t between 5 and 8. This is sounding like it's asking like one of our theorems of calculus, right? Does the data in the table support that between 5 and 8, the velocity is going to be negative 100? Between 5 and 8 is our velocity going to be negative 100. Looking at here, it looks like yes, because starting at t equals 5, our velocity is 40. At t equals 8, our velocity is negative 120. So does our velocity have to pass through negative 100 on that interval? It does if the function's continuous. Well, we know that v is differentiable, so it's got to be continuous. So we can say yes. So what can we do? This sounds like an IVT thing. We want to prove that a function passes through a given value. So we can say v sub a of t is continuous and differentiable. Remember, we have to state our conditions. It's continuous and differentiable. Then we can say v of 5. V of 5 is 40. V sub a of 8 is negative 120. And then we can say, we got to say that our number we're looking for is between that. So 40 is greater than negative 100 is greater than negative 120. Therefore, by the IVT, train A's velocity is negative 100 meters per minute for some t on 5 is less than t is less than 8. So this one was 2 points showing that our value is between our values here. That the value we're searching for, negative 100, is between the values that we know, and then using the IVT correctly in here. Okay? Cool. So 2 questions not relating to related rates, but good review nonetheless. Okay, let's move on to part C. C says, at time t equals 2, train A's position is 30 meters east of the origin station. Okay, so they're adding this little station thing on here. I'll go back to my diagram. Oh, it looks a little better this time. So let's say that this is the origin station. At time t equals 2, we know that train A's position is 300 meters east. I'll put that over here. 300 meters east of origin station. And the train is moving to the east. So the train happens to actually be moving to the east. Write an expression involving an integral that gives the position of train A in meters per second. Position of train A in meters from the origin station at time t equals 12. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at t equals 12. All right, this is interesting. This gives us what sounds like here, 300. That sounds like an initial position. Sounds like we know an initial position. T equals 2, P equals 300. And we want to know basically what is P of 12. What is the position at 12? Well, we're given some information about initial. We're given some information about the derivative of that function. This sounds like our final amount formula. That if I want P of 12, I'm going to need to find, okay, what is P of 2, the position I know, plus the integral from 2 to 12 of whatever that derivative is. In this case, we're talking about velocity is the derivative position of train A. Here we go. Take the initial position plus, remember, the integral from 2 to 12 of v. This will give us the change in position. If I put absolute value bars on the inside, it gives us the total distance traveled. But the integral from 2 to 12 of velocity gives us the change in position, right? Because the antiderivative velocity is positioned, and plug in 12, plug in 2 gives us how much the position has changed. All right, this is what I need to do. In other words, 300 plus the integral from 2 to 12 of v sub a of t dt. It said, write an expression involving an integral that gives the position of train A in meters from the origin at time t equals 12. This would do it, so that takes care of that part. This is my position expression. But then it says use a trapezoidal sum indicated using the subintervals indicated up here to actually approximate that position. Remember, trapezoidal sum approximates. Riemann sums approximate integrals. So I'll say 300, that'll stay the same, plus whatever my trapezoidal sum is going to give me for the integral from 2 to 12. 2 to 12, that's going to start here. There's 1 subinterval, 2 subintervals, 3 subintervals. Remember, for trapezoidal sum, we add together the outputs, 100 plus 40. We multiply by the delta t, or delta x. In this case, that is 3. 2 to 5 is 3. And then we divide by 2 all the time. Plus our next one. We add together for that next interval. Our output's 40 plus negative 120, so I'm just going to call it minus 120. Multiply by the delta t, 5 to 8, that's 3. That's the width. It's kind of like the height of our trapezoid, but with the width of our interval. And then divide by 2. Plus what we get on our last interval. We'll add together the outputs. That's negative 120 minus 150. Because it'd be negative 120 plus negative 150. And then multiply by that delta t, which is 4. 8 to 12 is 4. And then divide by 2. There's our trapezoidal approximation. We don't need to, remember, we don't need to do any simplifying. We can just leave things exactly like we see here. And so actually, I would just leave it like this because it covers everything. It gives us the actual position at t equals 12. It's 300. And then whatever we'd get over here, and it includes trapezoidal approximation. This is all we need right here. Does it say to include units? It does not actually. So you could leave things like this. If you actually simplify it down, you would find that this means that the position is negative 150. So negative 150, that means train A is 150 meters west, because it's negative now, west of origin station. Or I guess is approximately, is probably the better way to say that. Is approximately, because this is approximation, is approximately 150 meters west of origin station at t equals 12. If you wanted to go above and beyond and say that. All right. And lastly, question C. Oh, that was question C. Question D. All right. A second train, train B, okay, second train, travels north from origin station. So we got origin station. Second train travels north from origin station. At time t, the velocity of train B is given by this function here. And at time t equals 2, the train is 400 meters north of the station. Okay, time t equals 2, train is 400 meters north of the station at t equals 2. Find the rate in meters per minute at which the distance between train A and B is changing at time t equals 2. So this is how we start knowing things are related rates question. We're asked to find the rate at which something is changing at some time, right? We want to know a rate of change, and we're given some relationship we have to work out. So we have train B is traveling north. This is kind of tricky. Train B is traveling north. Train A we knew at time, what do we know about it at time t equals 2? Well, we got to go up here. At time t equals 2, we knew the train A's position over here. At times t equals 2 was 300, right? 300 at t equals 2. That was train A. Train B is up over here, going that direction. Train A is over here, going that direction. All right. So we want to find the rate in meters per minute at which the distance between the trains is changing. So the distance between the trains. So I've written out what kind of things I know. I know the distance between the trains. Ooh, this is going to be a little. Oh, I'm going to back up because that is not good. That did not look good at all. The distance between the trains is going to be that. It looks like we're going to make a triangle here, right? And the distance between the trains, then, is the hypotenuse of that triangle. So I kind of have my knowns listed out here. Let me write out what my unknown is. What do I want to know in the end? I want to find, let's give this a name. Let's give it, I'll call it h for hypotenuse. In the end here, I want to know h dt. What is the rate of change in the distance between the trains, right? So now I got to write an equation that relates what I have here. I know something about b going up, a coming out. I want to know something about dh dt. This looks like a Pythagorean theorem thing because I'm given distances, because really I know that this is 400. I really know that this over here is 400. I really know that this distance down here is 300, right? I'm going to call this distance over here, just to keep things straight, A, and this distance over here, B, to represent the position. So what do I know? I know that A squared, the distance train A is out there to the east, plus B squared, the distance train B is up there to the north, is going to equal whatever h squared is, right? Okay. Let me go ahead and take the derivative because I need to get down to dh dt. So this give me the derivative would be 2a, but with respect to time would be dA dt. Plus the derivative of b would be 2b, but b is changing over time. That position is changing over time, so we get dB dt, where b, remember, is the position of train B, equals 2h, but h is changing over time, dH dt. We got 2's everywhere. I can divide everything by 2, and to make this other change, dA dt. If A is the position, capital A is the position of train A, then dA dt is really the velocity of train A, right? How is A changing, the position of A changing over time? That's really velocity. So I can call this A, and then VA of t, plus, remember, I'm dividing all the 2's out, dividing everything by 2. B, that's the position of train B. dB dt, that's going to be the velocity of B, so that'll be V sub B of t, equals h, which I don't know, dH dt. All right. So what things do I know here? Okay, I know I want to find dH dt when a bunch of things are going on, right? So at t equals 2, what do I know? I know that A is 300. I know that B is 400. I also know that V sub A of t, when t equals 2, what do I know about the velocity of A? Well, I can come up to my chart. It is 100. Now, how can I find V sub B of t, right? Because I also would need that. Well, I need the velocity of B at t equals 2, right? That's really what I'm looking at here. So here's my velocity equation for B. So what is VB of t at t equals 2? I got to plug in 2. So if I plug in 2, I can come over here, V sub B of 2 equals -5. 2 squared is 4, plus 60 times 2 is 120, plus 25, right? So put all this stuff together, and I'll get 125. So the velocity, what is VB of t? The velocity of this train, B moving northward, is actually 125 meters per minute. Now I have everything I need here, sort of, right? Well, not everything yet, because I have A, VA, B, VB. I need to solve for dH dt, so I also need to know what h is. I need to know what the hypotenuse is. So let's go back to the Pythagorean theorem. I know that A is 300, that's the position of train A, plus train B, 400. Each of those will be squared in the Pythagorean theorem. Is going to equal the hypotenuse squared. So the square root of 300 squared plus 400 squared. But you might go, wait a minute. This is really just a 3, 4, 5 triangle, right? So that means that h is going to be 500. There we go. So now we do have everything that we need, okay? So I'm going to take this, bring it back over here, and say, all right, let me plug everything in here then. A, the position of train A is 300. That's how far out train A is. Its velocity is 100. Plus train B's position is 400 times its velocity, which is 125, is going to equal h, which is 500 dH dt. Now I need dH dt, so all I got to do is divide by 500. I'm not going to clean anything up. I'm going to leave this 300 times 100 plus 400 times 125 equals, I guess you say, over 500 equals dH dt. And whatever that is going to be the rate of change of the distance between train A and train B. Don't simplify it. If you do, you would find dH dt is going to be equal to 160 meters per minute. Yeah. Essentially what we're doing is we're recognizing that the trains make a triangle. Train A is moving out to the right, train B is moving up. A is the position, B is the position. Their derivatives are the velocities that I'm given in the table or in this equation here. I'm using Pythagorean theorem to find the distance between them. All right. Pretty good question, huh? All right. Let's take a look now at a free response question from last year, okay? This one screamed a little more quickly related rates. A cylindrical barrel with a diameter of 2 feet contains collected rainwater, as shown in the figure above. The water drains out through a valve, not shown at the bottom. The rate of change of the height h of the water in the barrel with respect to time t is modeled by this thing right here. All right. This is the rate of change of height, dh dt. They're giving us this, where h is measured in feet and t is measured in seconds. The volume of a cylinder is this thing here. We want to find the rate of change of water, of the volume of water, find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. This screams related rates to me. We're asked for a rate of change of something with respect to time when something is going on. So I'm going to do the work up here. I want to know the rate of change of the volume of the water. I want to know dv dt is what that sounds like. When the height of the water is 4. When h is 4. What other things do we know? Well, I know the rate of change of the height of the water is modeled by dh dt, which is negative 110 square root of h. Okay, what is some equation that relates v and h stuff? They give it to us here, the volume of a cylinder. The volume of a cylinder is pi r squared h. Now, if we took the derivative of this, we would have to treat r and h as separate variables, typically, that are both changing, right? And I would use the product rule. Pi r squared times dh dt plus 2 pi r dr dt times dh. I'd take the derivative of the second, keep the first, do our product rule thing. If r and h were both changing, I would need to do that. But this is a cylinder. My radius in here, as the water decreases, sure, h is going to change. But my radius of my water in the cylinder is not going to change. It's set because it's inside a cylinder with a set radius. So I can actually treat r like a constant here. And in fact, what is r? What do I know r is? R is not changing, so dr dt is going to be 0. R is going to be a constant of 1. Otherwise, when I took this derivative, I wouldn't need to worry about the product rule between r squared and h. So I'm going to go ahead and take the derivative to get to dv dt. dv dt equals, I want to treat r as a constant with 1. So I'm just going to plug in 1 in my mind. 1 squared is 1. So I'm just going to call this, so that's just pi. Really, then I guess I should say v is equal to pi h, because r is just 1 and it's constant. So what's the derivative of pi h now? Pi is a constant. It'll stay. The derivative of h with respect to time is dh dt. So what is this equal to? That's pi. Do I know dh dt? I do. It's negative 1/10 square root of h, right? And I want to know what is the volume, the rate of change of volume of the water in the barrel when the height, when h, is 4. That's relatively easy to do now, right? I know h is 4. So when h equals 4, I would get dv dt equals, I want to combine these negative, that'd be negative pi over 10 when I multiply that in. Negative pi over 10. The square root of h, square root of 4 is 2 times 2. It said indicate units of measure. I'm not going to simplify anything, I'm going to leave that. But what would the rate of change of volume be? Volume. So what are all my units here are feet. Volume is feet cubed. So that's the v part. But what is my time unit? What am I measuring time in? I'm measuring time in seconds. So it's going to be feet cubed per second. All right. There we go. If you simplify that, you get negative pi over 5 feet cubed per second. There we go. Pretty good question. Let's take a look at part B now. What does part B say? When the height of the water is 3 feet, is the rate of change of height of water with respect to time increasing or decreasing? Explain your reasoning. When the height of the water is 3 feet, is the rate of change of height, do I know what that is? I do. The rate of change of height, that is dh dt, right? So I can say this is dh dt increasing or decreasing is really what I want to know, right? Rate of change of height of water, that's dH dt. And I want to know, is dH dt, is the rate of change of height of the water increasing or decreasing? Okay. How do I know if a function is increasing or decreasing? I can look at its derivative, right? Well, what's the derivative of dH dt? I need the second derivative then, all right? Because if the second derivative is positive, that means the first derivative is increasing. If the second derivative is negative, that means the first derivative was decreasing. All right, so I can find the second derivative here if I know dH dt. Do I know dH dt? I do. They gave it to us in the problem. It's negative 1/10 square root of h. So I need to take the derivative of this. You can keep in mind that this is really negative 1/10 h to the half power. So what is the derivative of negative 1/10 h to the half power? With respect to time though, right? Because I'm going to take the derivative here. I'll bring down the half. That'll give me negative 1/20th h to the negative half power. But h is a function of time, right? I'm taking the derivative with respect to time. Taking the derivative with respect to time, right? So, what's the derivative of h with respect to time? dH dt. Right, everything is with respect to time. Taking the derivative of h with respect to time, I did the power rule and then chain ruled it to get it with respect to time. That looks like a minus. It should just be a times dH dt. Okay. So there's my derivative. That looks a little funny, so let's clean this up. Do I know what dH dt is? I do. I was given it. So I can plug what I know dH dt is in for that and change this. H to the negative half is 1 over square root of h. So I can call this negative 1 over 20 square root of h. dH dt is negative 1/10 square root of h. Interesting. I have square root of h down there. I have square root of h up here. So those will cancel out. And this will give me h, square root of h and square root of h will cancel out. Negative 1 times negative 1, that'll give me positive 1 over 20 times 10, 200. So I just found out the second derivative is 1/200th. What does that mean? I just found out that the second derivative is greater than 1, or it's not well, it's greater than 0 is probably the better thing to say here. Is greater than 0, right? Is greater than 0 for h is greater than 0, because it's like always going to be the second derivative is always going to be positive. It's just 1/200th. That's the second derivative. So the second derivative is greater than 0 for h is greater than 0, right? So the rate of change of height of water with respect to time is, so the second derivative was positive, so that means my first derivative, dH dt, the rate of change of height of water with respect to time, is increasing. I guess I could be more specific, say is increasing when h is 3. Even though that didn't really matter because we found out the second derivative was always positive. Again, we knew that dH dt, the rate of change of height, was increasing because the second derivative came out to be positive. All right, and last thing for us. At time t equals 0, the height of the water is 5 feet. This sounds like an initial condition. T equals 0, h is 5. Use separation of variables. We know that phrase. Define an expression for h in terms of t. Here is our big key, that this is a differential equation. I said we were going to review that, and we haven't really yet, so here it is. All right. Initial conditions right here. They give us that initial. We want to find an expression for h in terms of t. We give it in our initial. We know to solve a differential equation by separation of variables, we need an initial. We also need our differential equation. which is right here. If we want to find h in terms of t, we need to use a differential equation that has h and t in it. So dh dt equals negative 1/10 square root of h. I want to get h's together and t's away. So our normal process, we're going to divide square root of h over here. So that gives us 1 over square root of h. dh will stay over here. I'm going to multiply dt to the other side, so that'll be negative 1/10 multiply dt to the other side, dt. Divide by square root of h, multiply dt to the other side. Our h's are on the left, t's are on the right. That's what we like, right? We want to keep the variable that was in the top part of our derivative on the left. All right. Then once we separated, we do our antiderivatives. All right. 1 over square root of h, that's the same thing as h to the negative half, right? So we want to undo that. We want to find the antiderivative of h to the negative half. So I'll add 1 to the exponent. That'll give me positive half. Then I'll divide by the new exponent. Dividing by half is the same thing as multiplying by 2. Dividing by half is the same thing as multiplying by 2 because I add 1 to the exponent and then divide by half. There we go. Equals negative 1/10 dt. Well, there's no variable over here, so negative 1/10. Antiderivative of negative 1/10, we'll just get a t back. Don't forget the plus c. We always put it on the right-hand side just to keep things constant. Not meant to be a pun, but it kind of worked out. All right. So then I have my antiderivative. Now I can plug in my initial condition, which is 0, 5, right? So that'll be 2. I'm going to have 5 to the half power equals, well, t is 0, so that's going to be c, right? So this means that c is 2 times the square root of 5. There we go. I now know what c is. What does that mean for me? Well, coming back over here, that means 2 square root of h, because half power square root, is negative 1/10 t plus 2 square root of 5. I just need to solve for h, because I want h in terms of t. So I'm going to divide everything by 2. That'll give me square root of h equals negative 1/10 t plus 2 square root of 5 over 2. Remember, we don't have to make things look nice. If you wanted to, you could go ahead and call this like negative 1/20th and plus square root of 5 or something like that. But I'll leave it like that. We need to undo a square root, so we will just call that, we'll just kind of square everything, right? So that means h is equal to negative 1/10 t plus 2 square root of 5 over 2 quantity squared. And there we go. I've now solved for h in terms of t. If we want to, we can call this h of t over here if you would like. And there we go. Separation of variables to solve a differential equation. Cool. Hopefully this is a good review of related rates as well as reminders of differential equations. So what I'd like you to do is for homework, go ahead and try the 2 FRQs that are below. As usual, try them, score yourself with the work I'll put online, correct yourself, and submit the work and score report to me. There's another problem here, happens to also be related to a cylinder, and then a problem that is not related to related rates. It is a review of different topics. So this is just meant to keep spiraling in review for you of other topics we've covered already. It's a good question, some challenging stuff. Do the best you can with it and check your work. Please always reach out to me if you have questions. And don't forget to come by, starting today, Thursday, there will be review tutorials that Dr. Zarin and I are leading. Then you need to choose 2 over the next week. As well as tomorrow will be the first live class session. Okay? I will talk to you all later. Have a great day. Bye.